Imagine you look up at the night sky tonight, and somewhere inside our solar system, a black hole has suddenly appeared. No explosion, no warning, just an invisible object with gravity so powerful that even light cannot escape. What would happen next? Would Earth be destroyed instantly? Would the sun survive? And how much time would we actually have? When most of us picture a black hole entering our neighborhood, we imagine an escapable vortex tearing the planets apart within minutes. We assume it means instant, unavoidable death for the entire system. But that pop culture assumption gets the physics wrong. To know our actual fate, we have to look at the astrophysics of how these objects truly behave. First, we need to clear up the biggest myth of all. A black hole is not a cosmic vacuum cleaner. It does not actively roam around, sucking in planets like dust. Take a look at this simple balance scale. If you have a star and a black hole of the exact same mass, and you stand far enough away from them, their gravitational pull is identical. The concentric ripples of gravity they produce affect their surroundings in exactly the same way. That means surviving a black hole encounter doesn't require outrunning a vacuum. The danger depends entirely on two specific variables: the mass of the black hole and how far away it is from other objects. If we remove the idea of a cosmic monster and treat the black hole exactly as it is, a massive object with specific mathematical properties, we can calculate precisely how the end of the world would unfold. Let's run the first scenario by keeping the mass in our solar system exactly the same. Imagine a black hole with the precise mass of our sun instantly replaces the sun at the center of our system. This schematic shows what happens to the planets. The sun vanishes, replaced by the black hole, but Earth does not fall in. Because the mass is unchanged, the gravitational pull remains identical. Earth continues its usual orbit. Watch the same schematic though. Without the sun, visible light and radiant heat disappear instantly. The surface of our planet would plunge into darkness. Within days, global temperatures would drop below freezing. Over the coming months, plant life would die off. Ecosystems would collapse, and the upper layers of the oceans would freeze solid. The black hole wouldn't need to swallow Earth to destroy it. In this scenario, our planet survives gravitationally intact, but quietly becomes a frozen tomb. Now let's change the variables. Imagine the sun stays exactly where it is. A smaller, rogue black hole appears at the system's edge and begins moving closer to Earth. A tiny black hole out past Pluto wouldn't tear the solar system apart. But as the distance between Earth and the black hole decreases, the physical danger scales upward rapidly. As it approaches, Earth would experience tidal forces. You can think of this like pulling on a thick rubber band. If you pull one end harder than the other, the rubber stretches. This diagram shows those forces at work on a planetary scale. Gravity pulls significantly harder on the side of Earth facing the black hole than on the far side. The extreme difference in that pull begins physically stretching the planet. As the distortion increases, the collateral damage mounts. The gravitational interference would violently alter Earth's orbit around the sun. The moon's orbit would be heavily disturbed, and depending on the trajectory, our satellite could be ripped away entirely. It is proximity, rather than the mere presence of a black hole, that triggers catastrophic destruction. Distance is what turns a passive, heavy object into a planet-warping force. There's a practical problem here, though. If a black hole doesn't emit light, how would we even know it was approaching us in the dark? The black hole itself is completely dark, but any stray gas, dust, or material caught in its pull heats up violently as it falls inward, emitting enormous amounts of intense radiation that our telescopes can see. Even without fallen debris, a black hole betrays its location through a phenomenon called gravitational lensing. Watch how this invisible mass affects a field of background stars. Like a magnifying glass bends light passing through it, the extreme gravity of the black hole physically bends and distorts the starlight behind it. We wouldn't see the object itself, we would simply track the chaotic footprint it leaves on the fabric of space as it moves. So, if a rogue black hole passes through, does it eventually swallow everything in the solar system? Not necessarily. Objects can safely orbit a black hole forever, the exact same way planets orbit stars. This diagram of orbital trajectories shows how strict the physics of falling in actually are. To be consumed, a planet's trajectory and orbital energy must align on a highly specific path to cross the event horizon, the point of no return. The vast majority of paths simply loop around or slingshot away. The solar system wouldn't vanish down a drain. Depending on the speed and angle of the intruder, most planets would simply bypass it or be thrown into entirely new, chaotic orbits. A black hole with the mass of our sun replacing our star brings a slow, creeping freeze. A smaller black hole passing closely brings violent, stretching chaos. Science fiction often pictures a black hole as a localized delete button for reality, wiping out a solar system instantly. The actual physics point to specific, calculated climatic and gravitational consequences. When we understand the variables of mass and distance, a black hole stops being a magical cosmic monster. It becomes a predictable, albeit extreme, force of nature. A black hole appearing in our solar system wouldn't necessarily mean instant destruction. The true danger is, and always will be, dictated by mass and distance. And that's what makes black holes so fascinating. They don't need to suck anything in. Sometimes, gravity alone is enough to completely rewrite the fate of a solar system.